Yeah. Hi everyone, thanks for coming. Very excited for me to give a talk here. So my name is Dmitry Meshkov and I'm going to talk about blockchain, how it works. I'll make some brief introduction to blockchains. Maybe not all of you are familiar with it. And I will tell about Scorex, but very high level ideas about Scorex mainly. So I'll share our experience, how blockchains look like, what is their architecture, maybe high-level architecture, what are common patterns there, what can be different. And yeah, I'll first introduce myself, I think. I'm working in blockchain area since 2015 as a developer and as a researcher. So I found the cool project Scorex in 2015 when I left my previous job, and I liked it from scratch actually. And you know, we joined this IHK company. It's quite a big and well-known company in blockchain research. They mainly do research and prototyping, so it's like R&D laboratory, research and development, and idea of Scorex is that it's flexible and simple framework that allows you to create prototypes. So and it was very useful for these researchers from academias because actually now there is quite a big gap between theory and practice in cryptocurrencies, maybe everywhere, but in cryptocurrencies also. So a lot of good researchers, these academicals, create cool papers with proof of security and so on and so on. It should work absolutely good, but when you implement it, you found bugs. You found problems, you found bottlenecks, and actually to create something really cool, you need a few iterations through research and to development. The researchers should tell you what is the main idea, you implement it, you find bottlenecks, and you send it back to researchers and so on. So this is not just a one-step idea, it's a cycle. And now Scorex is not just a prototyping framework, it's now bigger because we have at least two blockchains based on it. First one I should mention is a Waves platform. It's like in top 10 cryptocurrencies right now with capitalization like $500 million and so on. They took our framework as a base. Now they rewrote it, but they took Scorex as a base and implemented all this stuff based on it. And the second production software based on Scorex is a Mantis client for Ethereum Classic. It's supported by IHK company, and it also uses different parts of Scorex in its Codebase. And actually now, since this year, just a few months ago, we decided that we have implemented quite a lot of good prototypes. We have cool ideas that complement each other, and we decided to create Ergo Platform that will combine all of these cool ideas we like in one blockchain. They complement each other, and you know, we already know how they work separately, but we should implement them all together. And its idea of Ergo Platform is to create, you know, better blockchain in all aspects. So we have better synchronization, better transactional language, better security, better economical model. So I was here at Crypto Economics and Security Conference, and I presented our economy model there. Actually, it's still in progress. We think about it. So yeah, that's me, and let me start with some blockchain introduction. How it works on the simplest example of Bitcoin, how Bitcoin works. because there are different now ideas. So the main problem that is solved by blockchain is a problem of double spending. So imagine Alice have a coin, and she creates two transactions. In the first, she sent this coin to Bob, and in the second, she sent this coin to Charlie. So separately, all these transactions are valid. So transaction from Alice to Bob is valid. Transaction from Alice to Charlie is also valid. But both of them are not valid because she have only one coin. Actually, she don't have two of them. And Bob and Charlie do not know each other, do not trust each other. It's a distributed system. Idea is to process such a situation in a totally distributed system, in a decentralized system where there is no central party. And in a centralized solution is quite simple. First transaction is valid. So if your bank see transaction from Alice to Bob, it accepts it, and then he will receive transaction from Alice to Charlie, and it will reject it. So a very simple idea, but in a decentralized world, it's quite difficult to order all the transactions by time, because you do not have actually timestamp in a decentralized world. And it's solved with a blockchain. So blockchain is just a chain of blocks, quite a simple definition. Yeah, so if we have blocks that have linked to parent blocks, every block has a link to a parent block, and now we actually have an order of transactions inside the block and between the blocks. So if we put them in such a data structure, you may regard it as a just linked list. It's quite easy to order these transactions, but a new problem arises: how to create these blocks, who can create these blocks, and how to deal with it. And first, before I start with this problem, with the solution, I need a mention of hash function. I think all of you know what is it actually, but I'll repeat a bit. The most important here is that it is one-way function. You have data of arbitrary length as an input, just a message, and you apply hash function to this message, and you receive a fixed length hash. And it's impossible to recover message. If you have a digest, you have a hash. You can create two different messages that leads to the same hash, and and actually hash is quite fast function, so it's very fast to compute hash. But when you have a hash, you know nothing about previous message, and you don't know how to create a message that will lead to such a hash. This property is used in proof of work. So it's a process how new block is created in Bitcoin. It's actually very simple. So we have a previous block. Yeah, here's at the left. We put hash of a previous block to a new block. We put some transactions to it. Every participant of this network do it on his local storage. It's different data for all of us. So imagine we have a network. Everyone is a participant here. So we all will may have different data here in transactions, but you on your own computer can validate them all. It's quite easy. You do not need to synchronize with others. And after that, you start to iterate through field nonce. It's a special field in a block. And you continue to do it until hash of all this block will start from a lot of zeros. So we'll follow some bit pattern. Now it's like 70 zeros in Bitcoin blocks. It's quite easy to estimate what you should do to create such a hash. You do not know what should be the message to create such a hash, you should iterate through different nonces and trying to find it with brute force, some kind of brute force. Yeah. So you choose some nonce and you receive some hash with probability 50%. Your first bit will be 0. With probability 25%, your two first bits will be 0. With probability 12.5%, your 3 bits will be 0, and so on. So now it's a very, very low probability to create a block, like 2 to the power of minus 70. It's a crazy number, actually. Good property here is that it's very easy to validate that all this big work was performed by user. So me as a validator, I can get this block, I hash it, I receive a message, I apply hash function to it, I receive a hash, and I can calculate number of zeros in the beginning. I do it very fast, and I understand that actually this guy who created this block performed a very, very big work. That's why it's called a proof of work, because you just validate a proof that someone performed very big work. And but actually, this block generation is a random process. We do it, all of us do it separately, and it may occur that I have created block 54 and broadcast it in a network. You should receive it, but with network latency, someone else in another part of the world created block 55, and there may be different transactions in these blocks. So block 54 have transaction from Alice to Bob, block 55 a transaction from Alice to Charlie, and we again do not understand what transaction is correct, who received this coin, and so on. But actually, rule here is quite simple. Correct chain is the longest chain, so there will be more blocks later, but correct chain is just the longest chain. At this point, we still do not know what is the correct block, these or these, but they all have a root at block 54. So we know that this chain may win, this chain may win, or this chain may win. It's like a random process, but in all of them, we'll have transaction from Alice to Bob, not a transaction from Alice to Charlie. And it's so-called eventual consistency. There is a well-known sub-theorem that in distributed system you can achieve 2 of 3 properties: consistency, availability, and partition tolerance. So blockchain solve this theorem in terms of eventual consistency. Right now you do not know the correct state. Our vision for current situation may be different, but our vision for some previous state, like a state an hour ago, is the same. It's very similar, like DNS, DNS infrastructure. So right now, these names may link to different IP addresses in different part of the world, but after some time, they will all send to, they will all link to the same IP address. So it's a block tree. It's a very important property of blockchain. You should always keep it in mind when you implement a blockchain or some application that use a blockchain, because while you receive some transaction in some block, in a recent block, you cannot accept it right now. You should wait a few confirmation. Well, it all depends. If you just get paid by coffee or small amount of money, you may risk. It may be okay for you then to risk a bit. But if you sell something very expensive, you'd better to wait few confirmations. To wait 10 minutes, 1 hour, If you'll wait 1 hour, you'll never. You may be sure that your transaction here is correct. It never occurred in Bitcoin history at such a long rollback. But this, rollback happens. They happens always, and you should always keep it in mind. And now that was some brief introduction to blockchain. Maybe if you have questions about this part, it's time to ask them. No? A lot of questions. Okay, well, let's.
What hashing algorithm does blockchain use?
It all depends. Hashing algorithm, So what hash algorithm that blockchain use? It all depends. In Bitcoin, they use SHA 256, and actually not just SHA, but double SHA so they twice applied to block. But in other blockchains, there are other hash functions, and here is quite a big problem that actually for SHA it's quite easy to implement ASICs, hardware devices that iterate through all these hashes very efficiently, thousands of times more efficient than your local computer. The commodity hardware. Actually, Bitcoin in his white paper it mentions something like 1 CPU, 1 vote. So it's assumed that every people in the world have a computer and they can join this network, and it will work until majority of the network is honest. So if majority of people on the world is honest, Bitcoin is secure. In practice, that's not true because of this hardware, and because Chinese guys know how to create this hardware very efficient, and most of computational power in terms of this hashing power is concentrated in China. And people don't like this and create a different algorithm of proof of work to be ASIC resistant. So to create such an algorithm, it's a challenge actually. It's not solved the problem, but it's a challenge to create such an algorithm that is probably secure to ASICs. It's impossible to create the specialized hardware that is much more efficient than your laptop. It's a commodity hardware, but it all depends. More questions?
So what is the mechanism by which you determine that 54 is the transaction that goes through and 55 gets written? Like in a typical transaction, the central banking system, the first transaction that goes through is the one that wins. What is it that determines the one that wins?
So the question is, what is the algorithm we decide what transaction is correct here? Yeah. So actually, I mentioned it. That's the algorithm. Only transactions in the longest chain are correct. If your transaction is not in the longest chain, it's removed. So here, transaction from Alice to Charlie is removed from blockchain. It's not on the longest chain. Actually, other nodes will just delete this block, and as if it was never occurred. So the rule here is quite simple. Correct chain is the longest chain, and if your transaction is not in the longest chain, it is not in a blockchain. More questions? Yeah.
What happens if valid transactions are in a shorter chain? Do they get rolled back, or are they also?
Excuse me.
If there is a valid transaction that's in a shorter chain.
Well, in this situation, I'm talking about situation that they are all valid. So both chains are valid. So this is valid, but they're different. If you just have an invalid transaction, like sending, if Alice will try to send 2 coins, well, she have only 1, this block will be ignored, and no one will accept it to the chain. So all these blocks are correct, all they are valid. There is no invalid block here. Yeah.
So I understand that if there becomes as the gap in between like first place longest chain and second place longest chain, as that gap widens, it becomes increasingly difficult for second place to catch up. But if that gap stays small, why are you convinced that there is eventual consistency? Why are you not convinced that this situation could continue indefinitely?
Well, it's a random process, yeah. And when you mine this,
So don't assume that everyone's friendly. Let's assume there's competition.
no. Yeah, I'll tell you. So here is the question is, why do we have inversional consistency, and why this situation won't be forever? So the only assumption I have is that majority is honest.
Okay.
So majority should be honest. Well, let's remove this block for now. Yeah. So even majority may be split between these two chains. Yeah, 50% mine here, 50% mine here. But it's a random process, and at some points, new block will occur. And when this block 61 will occur, majority will start. We will choose this chain. It's now correct. It's now the longest chain. So all the honest miners start to continue this chain. And even if you have a dishonest party here, he might try to continue shorter chain. But as far as he have minority of computational power, he'll create blocks more rare than honest parties. So anyway, in honest players will create more blocks and finally will win.
So in practice, how does the size of network latency compare to?
I can tell concrete numbers for these situations. Actually, in practice, it's not so, scarce. In Bitcoin, like 2% of blocks are orphaned, so in this fork, and are not in the main chain. So there is one such a block for 50 blocks in the best chain. So this situation is not realistic. It's just an example. Okay. And yes, sometimes there are forks of one length depth, and so the situation is we have like 2 blocks here, but at some point we'll have a new block here or here, and when we'll have block here, all the miners will switch to this chain. We'll abandon this block 55, and we'll start to continue chain starting from block 54.
It's also very, very low throughput, though, right? This is all experimentally verified at like 3 transactions per second.
Well, 3 transactions per second, it's a bit different number. It's not related to this stuff. Yeah, so if you're asking about throughput, it's it's related actually. Yeah, you are correct. So we need a block propagation to be very fast. We need all honest party to receive the next block like this block 56 very fast. And if block size is too big, it will go through the network for a long time. And while it goes through the network for a long time, other parties may create this block 57. Yeah, and concrete numbers in Bitcoin is like time interval between blocks is like 10 minutes, and the block size limit is 1 megabyte. So you should download 1 megabyte quite fast at the time that is much smaller than 10 minutes. That is quite easy actually. So that's it.
2 megabyte after the SegWit
2x? No. It's still 1 megabyte actually.
After the SegWit 2x?
Well, it's SegWit 2x is not completed. Now they have SegWit, but they do not have 2x. 2x will be in November. So it's in 2 parts. But yeah, it's another question actually. Yeah, right now block size limit is 1 megabyte. It's still 1 megabyte. Okay. Any more questions about this stuff? Yeah. Okay.
Why is it necessary to have this great amount of work done to get another block? Is that part of the trust aspect?
So, question: why should we do this proof of work to do this a lot of hashing to have such a simple ordering? Yeah. A problem here is we can do this stuff in terms if we have a majority. Yeah. So I already told it, we need like more than 50% of honest players. But the question here is that in a digital world, it's quite easy to create millions of different accounts that will look like different accounts. And if I'm the adversary, I can create million of accounts, and you can't tell whether it's 1 million of different people or it's just one me. Yeah, and so it's a protection to Sybil attacks. So here is in this design, you as an adversary can create a lot of patches for free. You are limited with your processor, your computational resources. There are other consensus mechanisms, not just a proof of work. There are proof of space that when your probability to create a block is equals to your space on the hard drive, yeah, proportional to your space on the hard drive. Proof of stake, when your probability to create a block is proportional to your balance, how much money do you have. And quite a lot of different consensus algorithm. Two most popular is proof of work and proof of stake. So proof of work do a lot of job. Yeah, nobody likes it actually. The second algorithm is proof of stake, where probability to create a block is proportional to number of your coins. So you can't create for free new computational resources, and you can create for free coins as an adversary. So it's all to protection Sybil attacks. If I am an attacker and I create a lot of digital instances of myself, it's not so easy to define a majority. Cool, let's continue maybe a bit closer to a code, because I can tell about blockchain itself for a lot of time. I want to talk about blockchain architecture. So what parts do we have in a blockchain and what do we do? So actually, blockchain is a network. Anyway, it's a network. And it's a P2P network. In the first assumption, it's one layer P2P network. So all the parties are at the same layer. That's not completely true in practice, but it's not so important here. And we'll go to discuss one node. What's inside one node? So first of all, it communicates to other nodes. Yeah, there are some requests to other nodes, and other nodes send some modifiers that change our local state, our local view of the world. In Scorex, we have a network controller that processes all these communications. You can just define what type of modifiers do you have and how to process them, where to send these messages. Every node have this network controller. And let's talk about different type of modifiers. And first, very common type of modifier is a transaction. So when we receive a transaction, what is the workload? What should we do? So I should mention here that actually transaction consists of two parts. First one is stateless So we should check that signature is valid, that the amount is positive, and so on. So it's like semantics of a transaction. You can do it anywhere. For example, at transaction deserialization from bytes. It's like a domain-driven design when you only have valid objects in it. Actually, it's not a good idea because signature validation is quite long, quite a long computation, and this may lead to quite a lot of DDoS attacks if you do it right after creation, and especially you don't want to do this stateless validation if you create a transaction from your local storage because you already made this validation. But it's possible to do it almost anywhere. The second part is stateful. You should check that sender actually have these coins at this point of time. So this stateless validation doesn't depend on time, while stateful validation is may change from time to time. So now this transaction is valid. After some time it's not, and so on. So we need a mention of state. We have a mention of state. So state is a current balances of all the parties in the network. So we put this, we send this transaction to state, and it checks whether it is correct or not. So here we have a mention of minimal state. It's a minimal data set required to validate arbitrary transaction. It's very important that this state should be synchronized between different nodes at the same block. If they have the same block, the state should be the same. And it depends on a blockchain. I maybe won't tell about this a lot of things, but actually it's like a map from your public key to your balance. So how much money do you have right now? When we state may be authenticated. It's a very cool feature, and it's implemented in some blockchains, including Ethereum. So we have a map from public key to balance, and we can create a Merkle tree on top of this data structure. It works quite simple. So we have elements of a tree. We put data to leaves, and we hash all the pairs. So we hash this pair, and we receive this hash. We hash this pair, we receive this hash, and then we hash these two hashes, and we receive a root hash. With such a design, it's called authenticated state. You can prove a balance of a chosen account. So we can just get some account A and provide this element and this hash, and it's enough to compute a root hash. You do not need all this data. You just need this top hash. And also in our work, we showed how to provide a proof of Merkle root changes. So it's possible to provide a proof that sender actually have these coins at this point of time, and state changed exactly as you expected. So if I send one coin to, if Alice sent one coin to Bob, you can check that all the things changed in a state, that Alice's balance become one coin less, and Bob's balance become one coin more. It's a cool feature. I'll tell about it a bit later. So we have a state. We check the transaction, and if it is correct, we send it to a mempool. Mempool is also a very common structure in a blockchain. It exists in all the blockchains. It's a storage of unconfirmed transactions. So it's a storage of transactions that are not in a blockchain yet. You just keep there in your local data structure. It's frequent modified, so usually it's kept in memory, and that's why it's called mempool. Sure, it has some limited size. It should be cleaned with some intervals. I'll tell about it a bit later. And yeah, all these data structures I'm talking about, we have in Scorex, and we have interfaces you should implement in your blockchain if you want to have it. And you'll have working blockchain. So we have interface for mempool, we have interface for state, we have some default implementations for some of these data structures. The idea is you can just define your transaction, define some, implement some interfaces, and you'll have working blockchain. So it's part of interface of mempool, what should be able to do. The more interesting example is a full block when you receive a block. So it's a block with all the transactions. First, you should send it to history. It's like a blockchain, but we have a mention of history because it's not just a blockchain. You need some more historical data here. So you send it to history. You verify that this block is valid in terms of proof of work. All you can validate in history you should validate. It's just a storage actually for some historical data, so you should be able to put this data with some validation, should return it by ID, and should provide some information to synchronize this history, because history should also be synchronized between different nodes in the network. After that, if your block is valid, you should actually check that transactions in it are correct, and actually apply this block to a state if it's in a best chain. If it's not in a best chain, you shouldn't apply it. If there is some rollback, you may roll back state to some step before. Yeah, if you have forks, you may require to roll back state to previous situation and apply few blocks more if you have a better chain now. So it's quite a strong communication here between state and history. Also, actually, you should send this block to mempool, and you should remove these transactions from a block from a mempool, so you do not need them. They are now confirmed that they are already in the blockchain. You should remove them from mempool. You may also remove some other transactions that become invalid. So if you have like this transaction from Alice to Bob and from Alice to Charlie, you can keep them all in a mempool, but after first transaction, second become invalid. In case of rollback, you should put transactions from rollback to block back to mempool. That's also quite important part of blockchain. And in addition, you should modify your wallet, because in Bitcoin, actually, you do not need just your private key to control all the money. You need some public data that can be computed from a blockchain. It's not a problem to get it, but you should know, well, like how much coins do you actually have. You have a private key to send, to sign transactions, but you should know how much coins do you have, how much transactions did you receive. And wallet is a storage of your private keys, of some indexes required for transaction creation. And also, we do not use a mention of wallet, we use a mention of vault, because we keep every local data to this storage. It's a storage of a local data. So, correct picture is such. So, this vault is different on all the nodes in the network. So these two parts, state and history, should be synchronized. Mempool should also be synchronized, but it's not strict requirement. It's better to have it synchronized through the network. And vault key is your local personal data. And so when you apply a full block, you should do a lot of stuff. You should check that block is valid in terms of proof of work, in terms of consensus. You should check that transactions in it are valid, save it to history, apply it to state. There may be some rollbacks in this at this step. Remove some transaction from mempool, add some transaction to mempool from rollback block, update your wallet. And what's important here is that all these operations should be done atomically. So you perform all of them or none of them. But it's very bad if you apply a block to history, but you do not apply it to state. Yeah, or you have a race condition or something like this. And that's why actually we have a node view holder. It's a central part of our node that communicates with these parts. It's like an interface here. So you in Scorex you just communicate with node view holder. You do not have direct access to these concrete parts, and this node view holder knows how to process different kind of modifier. And surprisingly, this node view holder is very similar in different blockchains. It doesn't matter what kind of blockchain do you use, what kind of transactions do you have. This workflow is the same, and actually it's possible to implement it almost all the parts of node view holder. And we have this implementation, so when you get Scorex, you should implement these parts, but you have central part already implemented. So it controls modifiers workflow, ensures that it's consistent, synchronize all the parts between different nodes, and yeah, it's similar for all the blockchains. Services, I haven't talked about miners or API or something like this. We do all this as a separate application. So if you need to mine blocks, you need to iterate from these hashes. It's a separate application, and it's quite common in all the proof of work blockchains, in Bitcoin, in Ethereum. Miner is a separate software. It's written on low-level language, and it communicates to your node through the API. So it's not built in your node. You don't need it included to your node because it's better to write it in some different language, maybe. The same for user API. It's also some additional part. It's out of this node. This node is what you need to download, process transactions, synchronize the network, and so on. Do I have some time? Let me check. Because this part is also quite interesting, because in Bitcoin and in Ethereum we do not have just a full block, as I told, not a block with all the transactions, but it is split in a block header and transactions. So it's an example from Bitcoin. So block header is just 80 bytes, and actually the rule we need to proof of work is that the hash of this block header should start from 70 zeros, not from the full block, just from block header. So you can just download this header, and you can check proof of work. You can check that work is done correctly without any transactions. After that, you can download transactions and check these transactions. There is a Merkle root of transactions here, so actually all the transactions are included here, but just a hash of them. You can't change transaction in the block, because if you'll change 1 byte here, all the hash will change and proof of work will be incorrect. So in Bitcoin they operate with headers. All you do with headers, you put it in history, and you can check that maybe you now have a best chain of headers. And this picture become more complicated because it's like an optimization, but very important optimization for blockchains, because actually mempool is more or less synchronized, and you do not need to download all these transactions again from other nodes. You do not need to download this full block with transactions. You just download header, you download transaction IDs, and you construct this full block from your mempool. You already have all of these transactions in your mempool. You already validated them, and so on. This is a very important optimization, because actually bottleneck in all the blockchain is a network. So we already had a question about throughput. Why do we have just 3 transactions per second in Bitcoin? It's just because network is limited. You can have a super fast software on your node. It's not a problem to write such a node that processes 1 million transactions per second on your laptop. It's possible, but you need to synchronize this 1 million transactions per second through the network. It's a distributed network. You don't send directly from one node to each other. You can have some intermediate steps. So the main problem in all the blockchains in terms of scalability is a network layer. You also should keep it in mind. You can't just increase the block size or decrease time interval between blocks, because you should be sure that your nodes are synchronized. And this kind of optimizations allows you to reduce network utilization, and most of the stuff done by a lot of researchers and developers is how to decrease network utilization in blockchains, how to synchronize with minimal network resources. I'll speak a bit about different node regimes. So we talked about full node that process everything, and that's cool. But what if you're just a regular user and you don't want to process all this blockchain? You are not a miner. You are not going to iterate through all these hashes. And for such cases in Bitcoin, there are light nodes or SPV nodes. They are quite quite simple, and actually they don't have a mempool and a state, because they do not validate transactions. They trust to other nodes. I should have, yeah. So they download just a chain of headers. They download their own transactions with a proof. I already told you about Merkle tree. So a proof of this transaction 1 is just these transactions and these 2 hashes. You do not need to download all the transactions. So they trust to proof of work majority. That may be quite a good assumption. It's usually possible to trust to majority, and you can quite fast synchronize with the network. You download just headers chain that is much smaller. Again, block header size is 80 bytes, and the block size is 1 megabyte. It's good. Use if you are going to use Bitcoin, use such an SPV wallet. Do not trust to some web wallets or third parties, because actually it's a big issue now in cryptocurrencies that users do not like to run their own node to validate even this proof of work. They go to some web wallet and trust to some centralized party, and if this web wallet will be compromised, your private keys will be stolen, your money will be lost. Actually, there is an example of such a behavior in Ethereum Classic. Their main web wallet was hijacked, and a lot of people lost their money. And when you go to web wallet, it can show you anything you had 50 coins, and it still shows you that you have 50 coins, but it already got your private key and sent this coin to adversary address, but you have an interface, you do not validate that you already have these 50 coins. But if you run SPV node, you validate that actually you have some coins, and you do not send your private keys to anyone. The last section here is a very fast synchronization. Actually, it's enough to download headers chain, just few last blocks, even if you're a miner, and you need a state. So you have downloaded this headers chain, you can download this few last blocks, but you need a state to start process these blocks. And fortunately, it's possible to download state if it's authenticated. I already told it in the beginning. So if state is authenticated, you can download its parts with a proof that they belong to the same path. Actually, it's the same what torrent clients do. They download your file in a parts with a proof that they belongs to this root hash. So in the beginning, you download the root hash of Merkle tree, and you download parts of your film with proofs that they belong to the same root hash to this film you are going to download. It's implemented in Ethereum, in Bitcoin, and in most of popular currencies. It's a mess to download all these blocks. In Ethereum, it will take you like a few weeks to process all the blocks from the beginning, so it's almost impossible. But in such a regime, you just need to download chain of headers and few full blocks. Yeah, so you download state chunks, state manifest, and recover state as arbitrary part of history. And that's almost all what I wanted to tell about today. So I already told that we have a framework to prototype different blockchains. We have interfaces for most common parts, for state, mempool, vault, and history. We have implemented some common parts like node view. You can find it on GitHub. It's written on Scala. And another good feature here is that common properties may be tested. So if we have a blockchain, so if we have some interfaces, we can test some common properties. Like, if you roll back block and apply it again, you are going to the same state. Yeah, it's quite a similar idea. And we have such a test kit now, where we have implemented quite a lot of properties. They are, such a high-level properties. It's like integrational tests for parts like mempool and state and history, and for all the nodes. So if you use our Scorex, don't miss that we have also a test kit that you have some tests for free, some property tests for free, that your blockchain actually works as it should. Do not have some security holes. So thank you for your attention. Here are my contacts. On SlideShare you'll see this presentation soon, and here are my organizations. Thank you. If you have any questions, ask please.
Do you want to show a little bit in the REPL how this works?
Excuse me?
Do you want to show the REPL how this works?
I may, yeah. Well, actually, I have just a small, yeah. So we have this Scorex framework, and we have some examples we have implemented. It's a full blockchain. The most, interesting example here is a hybrid example. It's an example of Twins coin. So it's a hybrid consensus protocol of proof of work plus proof of stake. It's a paper of Alex Chepernoy, and yeah, we have some test for him for it, but actually, yeah, I'll run them now. So it's an example how our test kit works. Not so beautiful, yeah. We left some debug output here. Yeah, but yeah, you know, when we have implemented all the interfaces and we launched the testnet, it worked quite fine. And we have this test kit. I like this idea so much, actually, because you know you can check some common properties for all the blockchains. Like you can double spend the transaction. If you have applied this transaction once, you can't apply it one more time. It's common for all the blockchains, and it doesn't depend on a type. If you've implemented our interfaces, they work. So yeah, these tests are quite long because they generate block, process block, rollbacks, and so on. And all these tests are property tests, so it creates a lot of rollbacks. Yeah, I can answer some questions while they're running. Okay, let's start with you.
So you know, I was looking at your GitHub, and I noticed really there are two versions right now. You're kind of in transition to the Scorex 2, and like there's a getting started for Scorex 1, but not yet for Scorex 2, that sort of thing. And I was wondering what should I, you know, in learning it, should I, you know, is it okay to look at the Scorex 1 stuff? Has it changed dramatically?
Well. Yeah, it's changed dramatically, so we have a major version changed. You'd better look at Scorex 2 for sure. We do not support Scorex 1 anymore, but yeah, you know, we played quite a lot with different parts, and we understood that our abstractions at Scorex 1 are not flexible enough for our purposes. Like it was impossible to implement such a hybrid protocol where you have a block of proof of work, then block of proof of stake. Yeah, unfortunately, it wasn't flexible enough, and it was based on some a bit incorrect assumptions there, and a bit wrong, you know, modular structure. So we now changed it. It worked quite good for quite simple examples. It's fine, but when we started to implement more complicated blockchains, we understood that it's not enough for us. And now we have Scorex 2, and we support it. I hope we will have quite a good quality framework soon when we'll use it actually in Ergo. So now we actively use it in a more or less production blockchain, so we'll improve quality, we'll improve performance, and so on. So,
have you used Akka extensively in your implementations?
What do you?
Akka?
Yeah, we use Akka for network layer. So it's I showed some kind of picture. It's a P2P network, and yeah, we use Akka quite quite a lot. Yeah, we send message. We use Akka IO to send messages between different nodes, and we actually send the same nodes inside a node, the same messages inside a node. So this node view holder is an Akka actor. Yeah, we use it. Yeah. Yeah.
How large the state can get?
How large the state can get? It all depends, as usual. Well, I can tell some examples. Like in Bitcoin, it's like 2 gigabytes. It's not so big. In Ethereum, I'm not remember, but it's like the same. size, but I should mention here quite a good example from Ethereum history. Like a year ago, they had an attack to Ethereum. So, state is very important because you should validate transactions fast. Because, well, if you have proof of work, you receive an e-block, and you should validate it, and then you'll start mine on top of this block, yeah? And while you validate a block, your hardware is stale, actually. You do not create a block because you do not know whether it's valid or not. In Bitcoin history, there was such an example when block validation took like 4 minutes on a regular hardware. It was a bad implementation, not optimal, but well, imagine that just the validation of a block took you 4 minutes. And you have a time interval like 10 minutes between blocks, and for 4 minutes, 40% of this time interval, your hardware is stale. It's not good. And in Ethereum a year ago, they had quite a beautiful attack, actually, DDoS attack based on this state. So there were 1 million of users at this point of time, and the adversary increased state size to 20 millions of users. So he created a lot of different accounts, and this state was kept in memory. For most devices, for most computers, state size became too big to be in memory. It was swapped on a drive. Its access time became very slow, yeah, and block validation took more time than time interval between blocks, actually, for like a month until they performed the hard work to fix this. So like a month, the network of Ethereum wasn't usable at all because of this DDoS attack. And yeah, after increasing this state size, the adversary began to touch random parts of this state. So he increased this state size, it swapped on the drive, and then he started to touch random elements from the state. So state is very important part of implementation. It should be very fast to validate transactions efficiently. Better to put it in the memory, but you should be ready for such DDoS attacks. Any more questions? Okay, then thank you for your attention.